Continuing this push from 2 dimensions to 3 dimensions, you'll recall that the dot product was an important feature we saw in vectors. A vector, whether it's in 2 dimensions, 3 dimensions, and theoretically you can keep going to 4, 5, 6, 7, you can keep going. It doesn't matter what it is, it's still just a line segment. That's what a vector is. So all the rules that we saw for the dot product, they're not going to change. They're still the same. So remember these. Assuming, of course, we're not talking about the zero vector. I probably should have put a tilde under those zeros to highlight we're not talking about the zero vector. There's our dot product. See, that's the beauty of using vectors for this stuff, is I don't have to worry about the dimensions because the dimension's like inside the vector. So the rule stays the same. It's, so u dot v will be magnitude of u times magnitude of v cosine theta, the angle between the two vectors. And theta, of course, could be acute or obtuse depending on the direction of the vectors. Now, if it turns out that either u or v is in fact the zero vector, then of course u dot v will end up being 0 because you're multiplying by 0. However, if it's not, another way we could find it, you remember if we got the actual column vectors there, well, then I just multiply the x with the x and the y with the y. That's what we did with 2 dimensions. So to push it through to 3 dimensions, we now multiply the z with the z. And that'll complete our dot product. So the properties of our dot product. Okay, we know it's always going to be in between these two values. And that's because it's times cos theta, and cos theta went between -1 and 1. So our answer should end up being somewhere in between minus the magnitude of multiplied together plus the magnitudes multiplied together. It does not matter which way round that you have them, because multiplication can be done in any order. So u dot v has got to be the same as v dot u. U dot u turns out to be the magnitude squared. And look, it's like expanding parentheses, but remember you're not actually doing multiplication, you're doing a dot product. So if you've got a vector dot product with a sum of 2 other vectors, you can treat it like expansion, but as I say, you're not actually multiplying. I'd say, oh, well, that's the same as a dot u plus a dot v. So similarly here, you'll see you end up with what looks like the difference of 2 squares, but again, we're not actually multiplying, we're saying u dot u minus v dot v. But from our property number 3 over there, we know, well, that's going to be the magnitude of u squared minus the magnitude of v squared. So it is very similar to the difference of 2 squares. If we're multiplying by some scalar, then it doesn't matter whether you multiply by the scalar second, which is on the right-hand side, found the dot product first, then multiply by the scalar, or if you prefer the left-hand side, you could multiply one of the vectors by the scalar, then do the dot product. It doesn't matter. This was an important feature. If it turns out that u dot v turns out to be 0, then that tells you the two vectors are perpendicular to each other. And if it does end up being one of those extremities, the positive or the negative of the magnitudes multiplied together, then you must have parallel vectors. How do you know which one? Well, if it's positive, then those vectors are going in the same direction. But if it's negative, then your vectors must be going in opposite directions. So A, B, and C are three-dimensional vectors. We're going to prove this property then. So we've got A dot B plus C. Let's put it in component form then. Because we know how to do the dot product, we'll just multiply the x with the x, the y with the y, and so on. So when I expand this one out, I'll get A1 times B1 plus C1 plus A2 times B2 plus C2, and then A3 times B3 plus C3. Expand that all out, but then when I group them, look at what I've ended up with. I've got A1 B1, A2 B2, A3 B3. Well, that's A dot B. And then in the second one, I've got A1 C1, A2 C2, A3 C3. Well, that's A dot C. So there's our proof that yes, indeed, that idea does work. We're going to prove that these two things are perpendicular. Same sort of question as we saw in 2 dimensions. Well, let's have a look at the dot product. 3 times -4, -2 times -8, 4 times -1. Yep, that equals 0. So equals 0. We know those vectors are perpendicular. So A is just some random point. We've given it coordinates A, B, C. And they've told us the angles it makes with each of the axes if we were to draw that plane in. Just going to show you something interesting here, which I'm going to use in the question. There's a vector in 2 dimensions. If I say that angle there is alpha and the other one is beta, well, cos squared alpha plus cos squared beta would be the same as saying cos squared alpha plus the cos squared of 90 minus alpha. But of course, cos 90 minus alpha is sine squared alpha, and that equals 1. So in 2 dimensions, when you've got a vector, one angle going to the x-axis, one angle going to the y-axis, the cosine of those squared should equal 1. Well, that's essentially what we're being asked to prove here in 3 dimensions. Though that's still going to equal 1 if we were to take each of those angles. So I'm going to say u is our vector that we're talking about there, but I've written it in component form. I want to find the angle it makes. Well, the first one I'm doing is the x-axis. So it'd be like saying what's the angle between the unit vector in the x direction, which is I, and our vector u. We know it's equal to a. So all right, u dot I, which we also know, is u, magnitude of u times magnitude of I times the cosine of alpha. Well, magnitude of u would be the square root of a squared plus b squared plus c squared times cosine of alpha. Therefore, if I play around with that, I can show that the cos squared alpha is a squared on a squared plus b squared plus c squared. But that's when I just look to the x-axis. Now, they're just random pronumerals I've used, so logically, cos squared beta, that's the one that's going to the y-axis, must end up being b squared on a squared plus b squared plus c squared. And cos squared gamma, that's the one going to the z-axis, must be c squared on a squared plus b squared plus c squared. So if I add the 3 together, we get a squared plus b squared plus c squared on a squared plus b squared plus c squared, which is 1. And that's what we wanted to prove. Let's play with a dot product.